In this video, we'll discuss about the properties of colloidal solutions. Now, what type of properties are having for colloids here? Already you know, colloids having many number of preparation methods. We discussed Bredik's method, baptization method, chemical methods. Now let me see the properties of the colloidal solution. There are various properties are there which are exhibited by the colloidal solution. If you observe that one, first thing is what? Colligative properties. Today morning we discussed these colligative properties. These properties are exhibited in which they depend upon only solute particles. So the properties which depends upon the number of solute particles, which depends upon the number of solute particles, are nothing but called colligative properties. So here colligative properties are as follows. One is osmotic pressure. The external pressure applied to the solution in order to stop the osmosis of solvent into solution. We call that one generally osmotic pressure. Now, what is osmosis here? The flow of the solvent through a semi-permeable membrane from dilute to concentration solution. Okay. Now, what is semi-permeable membrane, which allows only solvent but not the solute particles here? So this we discuss where in the solution topic. If you want any more discussion about this one, we'll discuss that one in the solutions. Next, lowering in vapor pressure, in which whenever you add some solute particles, the vapor pressure will be decreased. Then depression freezing point, when you add solute to the solvent, the freezing point of the solvent will decreases. Right? Elevation of boiling point, when you add solute to the solvent, the boiling point will be decreases. And all these properties comes under colligative properties, will be discussed in detail in the solution chapter. Next here, just like solutions, the colloidal particles are also exhibiting the colligative properties because they are big aggregates compared to the particles in the true solution. When you compare with the true solution, the colloidal particles are more than 1 nanometer size. Therefore, they can exhibit colligative properties. So when you observe the particle size of the colloidal particle and true solution particle size difference we are observing. This is for colloidal particle, this is for the true solution. So when you pass through semi-permeable membrane, isn't it? Colloidal particles cannot pass through the semi-permeable membrane actually. Why? Because of having large size in this case. Because of the large size. Because small size, when you pass through semi-permeable membrane, solvent and the solute both will pass through this semi-permeable membrane. But when you pass through the semi-permeable membrane, because of the high size of the colloidal particle, they cannot pass through the semi-permeable membrane. Only solvent will pass here, right? This is the difference you are going to observe. So we can conclude that number of particles in the colloidal solution is less than the number of particles in the true solution. So if we observe this diagram, what happened? The number of size, leave with that one. Number of particles here, how many here? 5 3 is 15 only. But here number of particles are how many? 3, 6, 9, 10. Then 1, 2, 3, 4, 5, 6, 7, 80 particles are there. Okay. Same solution, but number of particles are what here? More, it will be less here. So compared to true solution, the number of colligative particles will be what? Less here. So definitely, colligative properties will explain dilute solution, which number of particles are very less here. As we know, for a given number of solvent molecules, colligative properties are directly proportional to the number of solute particles. If you have more solute particles, then will be more elevation of boiling point, more differential freezing point, more osmotic pressure, more lowering of vapor pressure. So they are directly proportional. So hence the value of colligative property is small order as compared to the value of true solution at the same concentration. Before discussing the second property, let me take this one. If you take what camera projection, if you observe this one, when you go to cinema hall, you observe this type of projector here. This type of projector you are going to observe. Now, just imagine this projector now here. Have you noticed scattering of light beam while projecting a movie on screen? When this is projecting, what happened? This light will scatter spot. The light, this light is scattered by the dust particles. Whatever the dust particles are there in the atmosphere. How it happens that we see this. Camera is projected here. This is the camera projecting here. Something. You got something, what happened? A movie you're going to. But here what happened? Tyndall effect means what happened? The scattering of light by the colloidal particles is nothing but called Tyndall effect. So this you are observing. How you are observing? Because whatever the particles are there in the atmosphere, colloidal particles, dust particles, they scatters the light. So because of this, you are observing this type of beams you are observing. So let me take the Tyndall effect now. Tyndall effect is due to the fact that colloidal particles will scatter the light in all directions here. Okay, the Tyndall effect is because of the colloidal particles are scattering the light in all directions in the space. So that you are calling simply called Tyndall effect. Now let us see what happens in this. I have taken a true solution here, right? It's a true solution in which the particle size is less than 1 nanometer. The homogeneous solution, salt in water. Now it is placed in the darkness. No? When I place this one in the darkness, taken a light source. I have taken this is the light source. This is the light source. Now this light is passing through this true solution now. Now light source appears clear in the direction of light of the beam. So if you observe from here, what happened? So light, isn't it? Source appears, this light source, this one, appears clearly in the direction of light beam. Perfectly dark from direction of at right angle to the direction of the light beam. This is the right angle if you observe from here. If you observe from here. Perfectly dark from a direction, right angle to the direction of the light. This is the light beam and this is the right angle from which if you see what happened, it is what dark. Okay, now I am changing this one colloidal solution. Good solution now change to colloidal solution. The light source appears translucent in the direction of the beam of light. Here it appears as a translucent. Now when you see from the right angle, the direction of light, it shows mild, strong opalescence here, isn't it? That means you can it is visible for us. Is it visible? Yes, you observe this part here. This part is visible for us. Right? This is called what Tyndall effect. Now these have taken this is exhibited by the colloidal solutions as well as suspensions also. But we'll take colloidal solution now here, but not true solutions. I've taken colloid, I have taken source here. Now we are seeing under the microscope, everything we are seeing under the microscope by using the naked eye. Okay, by eye we are seeing this one. Now, when you pass light here, what is happening here? So one particle is there here, one colloidal particle is there. This is the colloidal particle. This colloidal particle will scatter the light in all directions like this. Light now scattered here, dispersed here, scattered like this. By whom actually? Colloidal particle. So scattering of this light in all directions in space, we're calling as what? Tyndall effect. Scattering of light beam is due to the fact that soul particle, colloidal particle, absorbs the light energy and then emit it in the space in all directions. So absorbing the energy and emitting in all directions, you are calling as what? A scattering of light. Absorbing the energy and emitting that in the all directions is called now scattering. See, this is the light actually coming from where? Light source. The light source, light is coming here, and this light, okay, when scattered by the dust particle or otherwise what happened, the colloidal particle, okay, then the light will be scattered, the light will be emitted in all directions. Now you are calling this one as a, this you can observe by, isn't it, by eye under using microscope. Now Tyndall effect is due to the fact that colloidal particles scatters the light in all directions in space here. This effect was first observed by the Faraday. Later it is developed, studied and everything by what? Tyndall. Therefore it is named as Tyndall effect. So what some condition must we have to follow to exhibit the Tyndall effect? All colloids do not exhibit Tyndall effect here. Now, what type of colloids we have to consider here? Now, first thing, the diameter of the dispersed particle is not much smaller than the wavelength of the light we are using. So what is the meaning of this one? The dispersed particle means colloidal particle, dispersion phase or colloidal particle. This colloidal particle is not much smaller than the wavelength of the light. So whatever the size of the particle, the size of what? Colloid particle. Colloid particle must be lesser than the size of the length, size of the light actually. So generally size of the light we show in terms of the lambda. You can take this one as a lambda. So the lambda of it means size of the colloidal particle must be lesser. Then only we get the Tyndall effect. Greater than, we don't get that. The refractive indices of the dispersion phase and dispersion medium differ greatly in magnitude here. They should not have same refractive indexes. They should have difference in their refractive index here. Now, what is this refractive index if you observe here? The ratio of velocity of light in a vacuum to velocity in specified medium actually. What is the velocity of that light in vacuum? Then what is the velocity in given medium? Then you take the ratio, you get this refractive indices, right? Tyndall effect is used to distinguish between the colloidal solution and the true solution. If they given what happened, true solution and the colloidal solution, you can easily distinguish by using Tyndall effect. So Tyndall effect is not given by the true solution. By the colloidal solution, it will be given here. So in this way, you can easily distinguish. And by using ultramicroscope, we can also get that. Colligative property depends upon what? Definitely, it will depend upon number of solute particles, and it depends upon what happened. Generally, what happened? It depends upon what number of solute particles, and but not the nature of the solvent. But not the nature of the solvent. So generally, what happened? I can take this one. Colligative properties among these. All are what happened? Colligative properties. Properties of next, some more properties we see color now. Let me take the color properties. Now, the color of the colloidal solution depends upon the wavelength of light which is scattered by the dispersed particles. So whatever the color you are going to get for the colloidal solution, that depends on the wavelength of the light which you are passing into the colloidal solution. Now what is the wavelength of light? Light rays will have what? Whenever light propagates in the form of wave, that waves will have different type of wavelengths, right? Now, so wavelength already you know this one. The distance between the two crest and tuff is nothing but called wavelength. Okay. Now different colors of light have different wavelengths. For example, when you observe 400 nanometers to 750 nanometer will exhibit by the color size. Okay, 400 nanometer to what? 750 nanometer. They exhibit various of type of colors. VIBGR, violet to what? Red. They exhibit different type of colors. If you want violet color, the wavelength of light must be like this. Then we get the violet color. If you want blue color, the wavelength of light must be what? 450 to 490. If you want green color, the wavelength must be 495 to 570 nanometer. If you want yellow color, the wavelength of light must be 570 to 590 nanometer. If you want orange color, the wavelength must be what? 590 to 620 nanometer. And finally, if you want red color, the wavelength must be 620 to 750 nanometer. So the light, whatever the color of the light is depend upon the wavelength of the light. Actually. The color of colloidal solution depends upon the wavelength of light which is scattered by the dispersed particles, colloidal particles. The wavelength of light depends upon the size and shape of the particle also. Okay. Now, the wavelength of light depends upon what actually? The size and shape of the particle. Now, colloidal particle size, if you observe, okay, when you take what? Finest gold sold red. For example, I have taken a finest gold particle. A finest gold particle I have taken, and that looks what? Red color. It looking what? Red color. Now, as the size increases, if when I increase this particle size now, Okay, when I increase this particle size now, that is now converting into, if you observe. First, if small size of gold particle, this is a small size of gold particle. Small size of what? Gold particle. Okay, atom, gold particle. Looking what? Red color. When the size of the gold particle is increasing, changing into what? You see, changing into what here? Purple, blue, and finally what happened? Gold and yellow. Whatever the gold we are seeing now here, whatever the gold you are seeing, this color is what exhibiting because of it is having large in size. So when you decrease the size of the particle of gold, it will convert into what actually? Red color because of small size. So the size, isn't it? The size of the colloidal particle, isn't it? Influencing the color size, right? Now, if you have spherical particle like this, spherical particle, it can scatter the light like this. So we are going to get what? Isn't it? Red color like this, red color because of scattering of light in the spherical light. When it is in the form of a disk type of structure, in this case, it can scatter like this. It can exhibit what? Blue color light. Shorter wavelength of light is scattered by the large particles and vice versa. So when you have larger wavelength, smaller particles, shorter wavelength, larger particles will scatter light. The color of colloidal solution also changes with the manner in which observes receives the light here. How the observer receives that light actually. For example, if I take what? Milk and water, which appears blue. Okay, milk, water is which type of solution? Which type of colloid? Milk plus water is which type of colloid? Emulsion. Best example, emulsion is. What is the best example for the emulsion? Milk plus water. Now, when it appears as a blue, when you view by the reflected light, when you view by the reflected light, it appears as a blue. When you view by what? Transmitted light. If you view transmitted light, it appears as a red color. Okay, when you view the transmitted light, milk and water. Okay, the emulsion of milk in water exhibited red color. If you view, isn't it? Reflected light, you are going to get the blue. That means observer how he receive the light. On that also it will depends. Wavelength of light depends on what? Isn't it? Size of the colloidal particle and shape of the colloidal particle. Some more properties we'll discuss. Brownian moment. It is very important. Both Tyndall effect and Brownian moment are very, very important. Let me see the Brownian moment here. Now I have taken an ultra microscope because it is visible under microscope only. Now these are the colloidal particles. Okay, these are the colloidal particles. How they are moving? They are moving in straight line? No, they are moving in zigzag structure like this. Like this, they are moving something. Okay, so the momentum, if you observe, of colloidal particles, they appear like zigzag structure. This can be observed under the microscope, ultra microscope. We can view this. So this zigzag momentum of colloidal particles is called what? Brownian momentum. The momentum of colloidal particles in the zigzag motion is called what? Brownian moment. This is what explained by the Robert Brown. So it is called what? Robert Brownian momentum actually. What is this use actually? Why? Because of Brownian moment, what we can explain actually. So this motion is independent of nature of the colloid. Whatever it colloid, whether it is a gold soul, or whether it is a dust in air, or whether it is in the gel, whether it is something what blood, everything, any colloid part, any colloid solution you take, any colloid you take, they exhibit this type of motion. They exhibit zigzag motion. They exhibit Brownian movement compulsion. Irrespective of nature of what colloid, they exhibit what? Brownian movement. Oh, but depends on the size of the particle and viscosity. But it should depend, whatever it may be, but it depends on what is the size of the particle. Okay, and what is the viscosity of the solution? Because if you have more viscosity, the momentum will be what? Decreases. Viscosity is nothing but what? The flow of what? Liquid, isn't it? When the flow is taking place like this, the flow of liquid is taking place like. So the front molecule is moving forward direction. The back molecule will, isn't it? Will pull this front molecule towards it. Because of this, what happened? The flow of the liquid is what? Retained here. Resisted here. Okay, the flow of the liquid is what? Resisted here. So resistance to the flow of liquid is called what? Viscosity. You take honey here. Honey is having viscosity when you compare with water. Water easily flows here, but in honey flows very slowly because it has some resistance to flow because of what? The intermolecular attractions between the molecules. So it can be concluded that smaller the size of the particle, lower the viscosity of solvent, make the Brownian moment very fast. So when you have lower viscosity, the momentum can be easily absorbed here. It can be easily undergo this type of momentum. Higher the viscosity, flow can be isn't resisted here. So they can't move like. So we should have lower viscosity to get the Brownian momentum actually. The prominent momentum is due to the unbalanced bombardment between the colloidal particles and the molecules of the dispersion medium. So why it is observed here? So whenever if you observe what happened, this momentum is taking place because what happened when the colloidal particles, if you observe what happened, they bombard with what happened, dispersion medium are together. You see, these two are bombarding with each other. Two particles are what getting bombarding with each other like this. Then they are bombarding with each other. Not only with each other, they also bombard with what happened, dispersion medium also. For example, you take water here. So when you add some what happened, then dispersion phase into this one, gold particles into this one. They gold particle will bombard with them, and also what happened, bombard with what even solvent also. So both are taking place. Now, do you know why colloidal Cellulose particles do not settle under gravity? So now why you are not getting a precipitation here? Isn't why they are not coming down here to give the precipitation? So Brownian momentum is main cause, isn't it? Main cause not to settling whatever the colloidal particles in the bottom. Because of this motion, what happened? These particles are not, isn't it, settling at the down actually. If this momentum is not there, they can settle it down and they will give suspensions. Now the colloids will convert into suspensions. So why they are not converting into suspensions? What is the reason? Because of what? Brownian momentum. Colloidal particles are stable. They're stable. They don't get any precipitation. Next, if you observe what happened, charge on colloidal particles. Next property, if you observe, charge on colloidal particles. What type of charge they are having? Why do they have charge? Why do colloidal particles will have charge? So when you observe colloidal particles always carry some electrical charge. If you observe what happened, they will have, isn't it, a charge within it. And why do they get? Let me see discuss. Right, let me see this one better. The nature of the charge is the same on all the particles in a given colloidal solution and may be either positive, either negative. For example, if I take a soul I have taken, whatever the particles we're having in that soul, all will have either positive or negative. Let me discuss something. A positive charged soul looks like this. This is the red part is you are observing. No, the red part is what? Positive charge. They're having a positive charge. So the red part is nothing but a colloidal particle. This is nothing but a colloid particle. Colloidal particle. The red part is you're calling as a colloidal particle, and the colloidal particles are having which charge beta? Positive charge. Solvent dispersion medium does not have any charge. Only colloidal particle dispersion phase will have charge, but not dispersion medium. You see, they're moving in the dispersion medium like this. Now, it may be hydrated metal oxide salts also. You take some examples, Al2O3X2. They may be positive colloids or nothing but aluminum oxide hydrated, chromium oxide hydrates, and oxides of iron hydrate. That means metal oxide hydrate. So which examples when we can take for positive colloids? Metal oxides with hydrated. Otherwise, hydrated metal oxides are the best examples for the positive colloids. Very, very important. Hydrated oxide, aluminum oxide hydrated, chromium oxide hydrated, iron oxide hydrated. These are the best examples for positive colloids. In examination, you can get this type of questions. Which are the following are, isn't it? Positive colloids. Now, some more examples I can take. Okay, basic dyes. Basic dyes can be taken as what? Positive colloids. Best example, methylene blue. Methylene blue is a dye It's a basic dye actually. So basic dye can be taken as positive colloid. And finally, we can take what happened. Hemoglobin comes under what actually, isn't it? Positive colloid, and even oxides also comes under positive colloid, like titanium oxide comes under positive colloids. So what type of examples we're having? Hydrated metal oxides, basic dyestuffs, hemoglobin oxides. Next, we will see the negative colloids here, in which the colloidal particle, if you observe, this is a colloidal particle having which charge? Negative charge here. Therefore, they are called negative colloidal particles here. Now, which type of examples we can take? Metal soles. Best example, gold soul, silver soul, copper souls, isn't it? Which prepared in by using Bredex method. They comes under negative colloids. Next, we can take what? Metallic sulfide soul, arsenic sulfide soul. See, arsenic sulfide soul, antimony sulfide soul, cadmium sulfide soul. They comes under what actually? Negative colloids here. And finally, acidic dyes. Basic dyes are what? Positive colloids. Acidic dyes are what? Negative colloids. What are the examples we can take? Eosin, Congo red soils can be considered as a acidic dyes actually. Okay. Next, if you see what happens, starch, gum, gelatin, clay, charcoal, these are all comes under as a negative colloids only. So you have to make a chart in which what happened, what are the examples for the negative, what are the example for the positive, and you have to remember that one for examination panel. Some MCQ questions. Brownian momentum is due to the bombardment of the particles giving zigzag structure. So answer will be what? A. Hemoglobin is best example for what? Example we can take it. Hemoglobin is for positive charge soul actually. The positive charge soul. About the charge of the colloids we have complete.